Looks like we're just about there. And it's official. It's week 2. Welcome back, everybody. Well, I hope you all had a great, restful holiday. It's kind of a shame for a Tuesday, Thursday class doesn't really affect us, but still we weren't on the hook for any coursework in our other classes on Monday. For today's class, we left just one problem in section 2.1. So we'll finish that one off, kind of revise what left-hand, right-hand limits look like on that last problem. And then look at the next content, just building on what we did conceptually in section 2.1 with algebraic methods. Same concept, but new tools. I have a couple of other announcements I want to make. The day-by-day syllabus has been revised, meaning the syllabus is the same, but the schedule has changed. And that was going back to a comment that I learned about on the first day of class. They changed chapter 1 a little bit, just the order of the topics, which was kind of weird. So if you go up to the top, any revision on the syllabus, always make an announcement and some kind of notification like this, revised. And this is the revision that landed on this syllabus. So just not chapter 1, but rather chapter 2 is affected. They changed the order of the topics just slightly. So these are the actual order of topics that we'll cover. Well, we're actually in 2.1, but this was reordered for what the syllabus would have actually been if I looked ahead of time and saw that topics were changed. So aside from that, no huge change in chapter 3, 4, 5, and 6, but I'm going to be double checking the new edition of the textbook before I release these notes, just to make sure they didn't make any big changes inside those sections. I know the section numbers are the same. So I'll be posting the notes piece by piece, just double checking we've got the right content, and we're not going off the rails, doing something differently than the book is doing. And the other big announcement I want to make is we'll be getting into a habit of weekly quizzes. And I'll be posting our very first quiz before we come back to class on Thursday. Probably I'll be posting them mainly on Wednesday since I have more free time. And my Tuesday, Thursdays are a little bit busy. But they'll be considered fully assigned on Thursday, and there'll be a full 1 week turnaround. They'll be due the next following Thursday. Oh, missed the chat, sorry. So the 2.2 and 2.3s are due this week. Not quite. There'll be their very first quiz assigned this week. There'll be like an assignment on the very bottom right here, and I'll show you what it looks like when it's posted. And then quiz number 1 will be due on the next week down below. So I won't have a quiz on each particular section. It'll pretty much just be one quiz on either one of the topics that we've been covering on the prior week up to that date. Other questions or comments so far? Yeah, so the web assignments are the ones that are going to be due on a section by section basis. Because we're finishing this one today, the due date has been revised. So the due date for that one is going to be on the 27th. Then the due date for this one will be on the 29th and so on. So just like also on the web assign and quizzes, there'll be a 1 week turnaround on the due dates for those as well. Well, there's other things I want to mention. You bet. Thanks for asking about those. For those other questions, or a lot of questions I've been getting so far are from people who are in the ISU's book bundle program. Oftentimes it's pretty seamless for this course, but this semester they're moving kind of slow. So I reached out to the people who are actually in charge, the Cengage people in charge of WebAssign, and this is the email I got. I usually don't post emails, but I felt like this was pretty relevant. So essentially, Josh Moore, he is our Cengage representative, says he's working on it. Says, thank you for letting me know. I was letting him know that people in the book bundle still don't show registered on WebAssign as they should be. Usually it's done by now. And the holiday wasn't enough to affect it. He says he's working on getting the paywall removed for the ISU book bundle students, so they do not need access codes. And he said something like along the lines that the issue stemmed from single term ISBN versus the multi-term ISBN. Strange, you'd think those are the same because it's the same textbook. This technology makes everything a little bit more complicated, but they should have that resolved soon. And I'm going to reach out on Friday to see what's going on. that still isn't completed. If you did opt out of the book bundle program, that can make a lot of sense depending on which courses you're taking. Make sure that when you go to register, that you go for the single term access. I believe it comes to $117. Let me know if that's off by $1 or $2. They, as the default option, this is kind of rude on WebAssign's part, they try to give you the multi-term access fee, which is very costly, but that's only if we were, say, using the same textbook over multiple different semesters, as some classes do. But we're only doing a one semester course on the textbook, so you should only be paying this access if you opted out. So there's the update so far about the book bundle. Sorry for the questions and confusion about that. In other courses, it's a little bit more seamless, but Cengage is just taking a while this semester. Other questions or comments so far then, at the moment? I think that was my major roundup of announcements. Okay, well, we're in section 2.1, and people have been working at WebAssign. Looks like just about everyone's registered, so thanks for being on top of that. Again, if any questions come up as you're working the homework at WebAssign, never hit to ask the Ask My Instructor button. I've been getting a lot of hits so far, so I'm happy to see that engagement. Some of them are just genuine questions, not sure how the problem goes or why an answer wasn't correct. And some people have asked questions along the lines of, well, they accepted this answer, but I felt like it didn't make sense. And those are great questions as well. So anything you want to talk about the problem, even if it's a follow-up discussion, I'll be happy to engage with you. And I'll talk a little bit more about WebAssign, maybe when we come back on next class. But in particular, when a due date goes past, I want to show you what that looks like, since there's opportunity to go back into a past due section and make up that work for full credit. But for the moment, we're in section 2.1, and here's where we left off. A big application problem, really not too big, but just a good way to tie together all the limits concepts we've been doing in this section with a pretty plausible scenario. So example 5, it says we have a patient who's receiving a 150 milligram injection of a drug every 4 hours. So some interesting drug infusion. We're not too sure what the treatment plan is for this. But we have a graph of what the concentration of that drug should look like in the bloodstream. The graph is going to be for the function f of t. So here's the f of t axis, the y equals f of t axis. Here we have a t-axis for time. And even though there is 5 different strips here, this is all just for one function, the amount of drug in the bloodstream after t hours. And kind of concerning about that drug is, notice it's elevating over time. So hopefully we're making sure it doesn't become a toxic level in the bloodstream at the same time. But this is our y equals f of t function. Notice it has some interesting discontinuities, open circles versus solid circles and so on. But also keep in mind when you see something like this isn't exactly what's going to go on in the bloodstream. This is just our best mathematical model of what we think the drug value should be inside your bloodstream. So this is our mathematical model for the amount of the drug. We don't expect it to be perfect. It's just our best attempt to model that drug in the bloodstream. And looking at it, it looks like what it's saying is the patient's receiving a 150 milligram injection. So at time 0 hours, there's an open circle here to say not all of that 150 milligrams actually goes into the bloodstream. How could that be? Well, maybe a little bit of it is left behind in the IV line or the needle or something along those lines. So we try to get right up to 150, but a trace amount just doesn't quite make it there. So we are just barely below. Time goes on, and right around the 4-hour mark, we have measured maybe it's 75 halfway down milligrams in the bloodstream, but they're due for injection every 4 hours. And so after that injection, it jumps up to a higher concentration, again with the open dot. It tapers off as the metabolism eliminates it out of the bloodstream, and so on, repeatedly over and over again, until maybe it stops after 24 hours or something along those lines. Well, what we want to do is evaluate two different limits. This one is a left-hand limit. We're taking the limit as time goes to 12, but only up to 12, not past the 12-hour mark. And the other one is taking the limit as time goes to 12 from the right. So we're looking at what happens as we get beyond 12 hours, but getting closer and closer to the 12-hour mark at the same time. We'll compute both of the limits, and really the big challenge in calculus is, after we evaluate the limits, we want to interpret what we see with those values and also pull in the context, the fact that this is a patient receiving an injection of blood, to say what's going on with both of those values. So there's two kinds of things going on around 12, the limit to the left, or the left-hand limit, and the limit coming in from the right, or the right-hand limit. All this is going to be relative around the 12-hour mark. So this is where we're most concerned. So let's just start writing out these limits. On the left, we'll take the limit. Time gets closer and closer to 12 hours from the left for the function f of t. Haley says, so the limit as t goes to 12 from the left equals 150. And the limit as t goes to 12 from the right equals 300. Yeah, absolutely. That's pretty much what the value for both of these limits are going to be. Looking at it from step by step, for doing this one on the left, that means we're tracking the time value as we get closer and closer to 12, coming in from the left again. Then the height of the curve is the amount of the drug in the bloodstream, but notice it's getting lower and lower. A lot of questions I did get is, what's going on with the solid dot versus the open dot? Turns out it doesn't even affect the limit one bit. Let's pause on that thought. Why does the solid dot there and open dot, or vice versa in a different graph, not affect the limit? It's because if we go to the very top of the notes, whether we're looking at the definition of a single-sided limit or double-sided limit, the value of the limit is not affected by what happens at A, 12 hours in this problem. We're wondering what happens around the 12-hour mark, not at 12 hours exactly. Haley says, I wonder what the use would be for reading it from the right. Yeah, that's a great question. We'll try to address that as well as we go to the interpretation side of this. But so far, on the left-hand limit, like you said, we're getting closer and closer to a value of 150. So we'll say that this limit is 150 milligrams. We'll put down interpretation on that one, and the same for this one as well. So let's write in this limit next. Limit as time gets closer and closer to the 12-hour mark. But we're assuming we're beyond the 12 hours. We want to know what happens just around that time. So we're looking at a different limit. We're coming in from the right in that direction. Let's move up, hit the curve. We're coming in from the right. Notice the values are getting higher and higher because we're getting closer and closer to that 12-hour mark where an injection happened and the amount of the drug spiked in that patient's bloodstream. So we try to scroll just a little bit. There we go. Looks like it gets getting closer and closer to 300, as was mentioned in the chat. So we'll say that the limit for the amount of blood, f of t, is going to be 300 milligrams. It's kind of weird because I want to think of this as a concentration, milligrams per liters of blood, something like that. But this is just strictly the amount of drug itself, not as a concentration, just a absolute amount. Well, we got the limits down. Last thing we need to do is just give an interpretation on both of them to say what it means in context. Let me make sure that the color coding sort of matched up for both of them. Any questions at all, folks? Just getting the values down, the 150 with or without the unit and the 300. Okay, actually wanted to leave that there just to convey how we got those values. Well, the big question is, what would you say about this one Let's start on the interpretation for the one on the left. We can say as we get closer and closer to the injection, at the 12-hour mark, this is conveying the direction because we haven't had an ejection yet. An ejection means it would have spiked up. We're just getting closer and closer to that time. We can say next that the amount of blood, or excuse me, the amount of drug in the blood is getting closer and closer, dropping closer and closer to 150 milligrams. The amount of drug is getting closer and closer to 150 milligrams, whatever that drug happens to be. Maybe you could imagine this is, say, a burn unit. This is pain level care, and you might have an morphine injection, but they don't want you to overdose, so you're locked out every 4 hours. But right at the 4-hour mark, that's when you're really hurting, really feeling it. The drug is getting lower in your bloodstream. You click it at the 4-hour mark, and it jumps up. Or any other kind of related context. Doesn't have to be pain management in a burn unit. That's kind of morbid. Could be something along the lines of maybe you have a nasty antibacterial infection, and this is a heavy-duty antibiotic, something along those lines. So what's happening on this limit right here? Well, we can pretty much say the same sort of thing, but we're just talking after the injection. So we can say as we get closer and closer to the time after the injection, the amount of the blood in the bloodstream is getting closer and closer to the 300 milligram level. Haley says the amount of medication in the patient after receiving the shot at 12 hours is 300. Yeah, I think that would be a great way to say that. Say if that was a response on a quiz or exam, I would give full credit for that. It's mentioning the values, it's mentioning the context where you said the amount of medication in the patient, and so that'd be a great answer to that. So let's put down something along those lines as we get closer. And closer to the 12-hour mark after the injection. Sometimes when I write a lot, my penmanship kind of takes a nosedive. Let me fix that a bit. As we get closer and closer to the 12-hour mark after the injection, we're after, so we're to the right of 12 hours. The amount is getting closer and closer to the 300 milligrams, as you said. The amount of drug is getting closer and closer to 300 milligrams. And that'd be one take on it. You might have a slightly different way to interpret this, as long as you're mentioning the key details, the fact that as we approach a certain time from a certain direction, a level is approaching a certain amount, getting closer and closer to 150, you'd give full credit for that kind of response. So you don't have to use the exact wording that I put down here. Just capture the major essence to mention the context, mention the fact that we're talking about injections, and amount of drug in a patient's bloodstream. Well, that was our start to calculus, section 2.1, thinking about limits, but really more conceptually looking into graphs. In 2.2, like I mentioned, it's the same topic, but we're going to get some additional tools on working these kinds of limits. So we can answer the question of how would we find the limit if it wasn't a graph given? Maybe it was a formula for f of t. We should still be able to compute that limit without plotting out a graph. And that's what we're going to be doing next section. Any last questions then, folks, before we turn over to that next section? Okay, I want to scroll to just a random spot on these notes that's going to come back in that next section. Pretty close to the top, right about here. So we'll take another look into these three interesting limits as it relates to the next section. The next section looks kind of awful. It's sort of overwhelming to open a section like this and see limit laws that go from 1 through 11. That's a lot of material. But keep in mind, when it comes to limit laws, here's a really big analogy. This is kind of like exponent laws. There are about, I'd say, 15 to 20 exponent laws you could write down on paper if you're writing down all of them. But the goal is to become very familiar with them so you take those properties for granted. We'll be doing the same things with the limit laws that we see here. Yeah, I agree, it's quite a lot. Another thing to keep in mind is when it comes to exams, I put on the very last page of exams formulas and things like these, limit laws that you can use in the exam itself. So this is something I probably would put on our very first exam, just the statement of limit laws as a resource. Well, first, just some initial topics before we jump into these notes. There's really three big concepts when it comes to calculus. Continuity, that's the very next section, 2.3, and we've been making small hints all along the way as we get closer to that section. Differentiability, that's a heck of a word, but that's in chapter 3. And the idea about differentiability is we're really interested in slopes, in particular slopes of tangent lines. And the next big concept is integrability. That's another weird word, but in short, that's just going to be areas under curves. Every one of these concepts are defined in terms of a limit in some way, somehow. We'll see shortly in the next section, maybe next class, how it works with continuity. So if all the interesting things in calculus are defined by limits, means we just have to face our fears, get through the limits, see how they work. They're pretty weird topics, but I think you'll feel like if you can understand them conceptually, what's going on in the graphs, and the way we'll do it algebraically, won't feel too different from just other algebraic topics. It just gets wrapped together with a limit. And here are the limit laws next. So LL just stands for limit law. It goes from 1 through 11. The idea is we assume we have two different functions, f of x and g of x. The limits of both of those functions exist, so they come out as a finite number. Then if you did something to the functions, just say add them together and take the limit, you can break up that limit. The limit of f of x plus g of x is the limit of f of x plus the limit of g of x. If you're subtracting, same kind of idea. If you multiply the function by a value, say like 5, well, you just take the limit of the function and multiply by 5, and so on down the line. There's a lot of stuff here. So part of our goal in these notes is just to break these down. We're going to cite these as we go. So this might be a good page to have kind of just at the ready, maybe on a different screen, maybe on a printout, have this page ready. I'll be pulling up this as my quick shorthand. We'll look at them in context as we go through the problems. Even though we're doing this with algebraic methods, this is so much new stuff out of nowhere that we're actually going to start off with a graph problem. So sorry to folks who might not be too happy going back to the graphs. It seems like a natural place to investigate all these brand new limit laws. After we get a handle on that, this is going to be our massive tool right here. This is going to show us how to do limits in this way, purely algebraic. So we'll work our way towards there with the goal of just digesting this material. You can't look at a wall of limit laws without taking some time with them before we use them in context on these problems. So let's start off here. We have the graphs of two different functions given, much like the f of x and the g of x that's provided in all these limit laws we see. On the left is a graph of f of x, on the right is the graph of g of x, and they have some small issues. There's a hole in the graph right here, and the function value defines 2 units above. A hole here, and the function is undefined at 2. And this one does an entire jump, and then hits a corner and goes down. So two pretty bizarre looking functions. It says for the two graphs given, use them to evaluate each one of these 6 limits if they exist. If the limit fails to exist, we'll explain why. So this is a pretty good recap of section 2.1 as well. And if a limit law is used, we'll cite the law used. So this is the big thing that we're doing in these notes, again, just as a vehicle for digesting these limit laws we see right here. So let's start off in stages. Let's go top to bottom, left to right. First one is we're taking the limit as x goes towards 2. So we're very interested in the value 2 on both of the x-axis for the function f of x plus g of x. Limit law 1 says you don't have to look at what would happen if you add these functions together. You can divide this up and analyze the set limit separately. So this is limit law 1. Let's write it in and make a note. Just choosing a color, sorry. Here we go. This is going to be by limit law 1. We can rewrite this whole thing as the limit as x goes to 2 for f of x plus the limit as x goes to 2 for g of x, and just work from there. Let's color code this just to help our eyes see where to look on each one of these. So now it's effectively just 2 problems duct taped together through the addition sign. So the addition here breaks apart. In a certain sense, it's almost as if the limit operator just has a kind of distributive property. It can distribute across addition in that sort of sense. Now we just do 2 limits. Let's go carefully. When it says x is 2, we are right here on both of those axes. For the f of x function, we're getting lower and lower on both sides, getting closer and closer to a value of -1, right where the open circle is. So for f of x, we get -1. I'll keep that in blue to say we got it from the f graph. And then for the g of x graph, we're going towards 2. This one doesn't have any weird behavior. There's a corner, but that's no big deal. There's no open circle or other problems. As we get closer and closer to +2 on the x-axis, either from the left or the right, height of the curve gets closer and closer to +2 as well. So let's say the limit on this one is just 2 itself. And so the value on this whole thing is a limit of 1. So now our work is done, and this is pretty much the name of the game. We'll see a problem like this one in the section 2.2 notes as well. Any questions or comments at all, folks, getting through this one? Let me fix that penmanship there. That was meant to say limit law number 1. Okay, let's try this out again. Moving to this one, we're taking a limit as x goes towards 0. Let me zoom in just a bit so we can really see this. I'll zoom in a whole bunch so we can hide the ones below as well. We're taking the limit as x gets closer and closer to 0. That means on both graphs, we are concerned right around here on the x-axis and here on this x-axis as well. We want the limit of f of x minus g of x. You know, sometimes on these problems, it's a good idea to look before you leap on these. We can take the limit of the f function. It gets closer and closer to 2 as we get closer and closer to 0. But what about the g of x function? What would you all say the limit should be for the limit as x tends to 0 for g of x? Haley says does not exist. And yeah, that's true on this one. This one's a pretty tricky limit. If we're coming in from the left, you're absolutely right. We're getting higher and higher, reaching a value of 3. But remember, the solid dots and open dots, they don't affect the limit. What will affect the limit is the type of limit we're taking. So let me write down a quick comment. It is true that as we take the limit, as x goes to 0, but only from the left-hand side, so put a superscript negative sign, the value of f of x gets closer and closer to 3. But as we come in from the left, it gets closer and closer to something different, a 1. So now we get to say the limit as x goes to 0 of g of x does not exist, or the shorthand used in chat, DNE. You have to explain why, but the short verbal answer is the limit is 3 if we're coming in from the left. That's this limit right here. But the limit is 1 if we're coming in from the right. So we can say very briefly, if you ever have to explain yourself, say on a quiz or exam, all you really need to say is the left hand and right hand limits are different. You're getting different values depending on the direction you came in as. There's a big jump or break in the graph in this way. It's just that it does not exist. So the limit laws actually don't help us. Sure, the limit laws say you can subtract in this way, but look what else it says on the limit laws. Both of the limits had to exist in the very first place, but the g of x limit failed to exist. So this law does not apply this time. The only answer we can give to the whole process on this one is does not exist. So in other words, if you're taking a limit and one or the other graph has a does not exist, the whole problem itself is damaged. The answer is just does not exist overall. So we didn't use a limit law on this one. We just used a property from the section 2.1 notes. So we'll move on to the next one. But any questions with the second version or second problem so far? Okay, let's try this out again. This time we're multiplying the functions, but the way we got that does not exist means we should be really careful about where are we going on the limit. This time, the action is all about around -1. So on the f of x graph, we're concerned about what happens around here. And on the g of x graph, we were wondering what happens in that region right there relative to that limit. Also, we need limit laws. So here's the superstar for the section 2.2 notes. The limit law says, if you're multiplying functions, there is yet another kind of distributive property. The limit of f of x times g of x is the limit of f of x times the limit of g of x. So once again, we can just divide and conquer, take the limits independently. So yet another kind of distributive property distributes in this kind of way. And we have limit x tends towards -1 of f of x, multiplying, I'll put a little dot here for multiplication, limit x tends towards -1 for g of x. These limits are both defined this time. Notice the funny behavior right around here for the f of x graph. Actually, that was our very first example, number 1 in the section 2.1 notes. Recall the limit is totally unaffected by whatever happens at -1. All we really care about is what happens around -1. That means there's a kind of interesting strategy you could take. If this dot right here kind of distracts you, you could say take a thin vertical strip or maybe a string, something like that, and just override everything right over here. Just hide this information from your eyes, because everything right at -1 is irrelevant. It's all about what happens around -1. If you're coming in from the left, it's getting closer and closer to a +1. If you're coming in from the right, it's also getting closer and closer to +1. So that limit for f of x, let me fix this first. The limit for f of x equals 1. We'll multiply it by something, the limit for g of x. We take off this strip, which is kind of a blinder, so we're not distracted. We have a value of 2, but again, the limit doesn't depend on what that dot's height is, or if it's present at all. It could just be gone, and the function's undefined at -1. Now we need to turn it over to the g of x. Anyone see the limit as x gets closer and closer to -1 on g of x? Oh, just missed a chat, sorry. Yeah, absolutely, Trayson. That one will get closer and closer to a 2. Here's a way to think about it. Again, it's all about where is x going? But it's a busier problem visually, right? Because now there's two graphs at the same time. So you also have to ask yourself, well, which function are you working on? So if we're getting closer and closer to -1 on the g of x function, it means all you care about is the height of the curve around here. If you're coming in from the left, you're getting closer and closer to those heights, which are around heights 2. But if you're coming in from the right-hand side, it's falling, 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 but it's getting closer and closer to the same value on either side. If we're getting closer and closer to 2 on both sides, the limit does exist, so we put down a value of 2 on this one. Then our work is done. The value comes out as a 2. I noticed I did forget to say one thing. It said if a limit law is used, cite the law used. We're really just doing this for the sake of the notes. We used limit law 4, so let's just put this down as a paper trail in the notes. What did we use on this line? Limit law number 4. I won't ask you on exams or quizzes to document every formula that you used. Again, this is mainly for the sake of the notes. So that's 2 limit laws we've used so far. Let's now take a look into the next grouping of problems. Let's see if we can zoom out just a tad, maybe bring these up a little bit, and try the next version. Well, over here, we're not taking the limit. Sorry, just trying to get more vertical space as x goes to 3. So let's change our focus around. On the x-axis, it's all about 1, 2, everything right around here where the yellow highlighting is to match the direction of the limit. It's f of x over g of x. If we take this step here and write out it's the same thing as, let's take a look at our laws so we're not just writing down something random. Here's limit law. Hang on, I think I made a mistake. No, we're good. Limit law 4. Limit law 5 says if you're taking the limit as x tends to a number a of f of x over g of x, it distributes across a fraction as well into the numerator and the denominator. You take the limit of the same values and you get a number out. As long as the limit of g of x as x tends to a is not equal to 0, because we still can divide by 0 in this situation as well. So let's call this limit law 5, what we're about to use. We can rewrite this as limit as x tends to 3, the function f of x. Should always be nervous when we write down a fraction though, right? So let's see what happens on this one. Divide by the limit as x tends to 3 of g of x. Your training in algebra is still relevant. This is a fraction. So if you happen to have gotten a value of 0 in that denominator, the response to this one is does not exist. And that's what the limit laws are saying. This is the right value as long as we get a non-zero value for the denominator. That means we should look at the g of x function first. Okay, here's g of x. We're going towards 3 on the x-axis, so look at where the yellow highlighting is. But as you get closer and closer to 3, values are getting closer and closer to 0. The height is right here, 0 on the x-axis. And that's true whether you're coming in from above or coming in from below. And so this one is yet another does not exist. We wrote down this step only because, well, emphasizing limit law 5. If you skipped this and just said does not exist, put in the explanation, that'd have been a great way to do this problem as well. Well, let's say it's right here, does not exist. Well, let me scroll a little bit so we don't have to feel like we're cramming it in. Does not exist because limit as x tends to 3 of g of x equals 0 on this one. Emily says, will we get a limit law sheet on the tests and quizzes, or do we need to memorize them all? Yeah, I do put this particular limit law sheet. this one right here, the full thing, not kind of clipped and compressed like you see here, on exams. As far as quizzes go, quizzes are take-home quizzes. So when you go to do your quiz, they're really open. I call them quizzes so that they don't sound the same as website homework. The quizzes you can ask questions on for people in the class. You can ask me questions, and all material available on Canvas, we open Canvas, including the notes in this section, are available for you to use to get through that quiz. And yeah, I understand what you're saying too. I mean, this is a lot of stuff to digest out of nowhere. And so you're not expected to have perfect memorization on all of this. It's more about, are you able to use the limit laws in the right context? Well, that's a couple down. Let me just zoom out a touch so we can see the whole graph and the response on this one in screen. Okay, all right, I think it's barely on there. Let's change gears to the penultimate problem. This one's different, right? There are two functions. There's an x squared function and an f of x function. So it feels strange at first, but x squared is a function just like an f of x times a g of x is a function. We can just straight out use limit law 4 and break out this problem by saying this is the limit as x tends to 2 for x squared times the limit as x tends to 2 of f of x. The blue function comes up. So I'm going to use multiple limit laws on this one. On this one, we had two functions multiplying x squared times f of x. That means we used limit law 4. In place of f of x, think of that as the x squared. In place of g of x, think of that as the original f of x in the problem. And x squared went here, f of x went right here. So let's cite that one. That's limit law number 4 to start out. LL4. And certainly we can take the limit as x goes to 2 for f of x. The mysterious one is the x squared. We actually haven't done that right just yet. So that's what this section is all about, doing the limit for a function like x squared without pulling up its graph. If we did pull up the graph, that's not a bad way to do it. But we have extra tools this time, so let's scroll through what we've got. So we've been working 1 through 5 so far. Limit law 3 hasn't come up so far, but it will. We'll cite it when it happens. The limit of a constant is just the constant. So if there's no x's there, you take a limit. That's kind of nice. You just get the number that was on the inside. If it's x and you take the limit as x tends towards a, you're just filling in an a and getting that as an output. And if it's x power of n, say x squared, that's the one that finally matches up. If it's x power of n, all you're doing is you're taking the value x tends towards a and plugging it in. We're going to later call that a direct substitution in these notes. So if you're taking the limit as x goes to 2 for x squared, you just plug in a 2 right here. Let me put in a temporary annotation, just visualize that. 2 is going to go into that side there for x squared. Much like a limit law 9, a goes inside of x power of n, resulting in a power of n. So that's a kind of a nice limit. It does not work for every single function, unfortunately, but when it works nice. So limit law 9 is a great property. Any questions about it so far? Okay, let's give it a try. And let me clear the annotations. We're going to use limit law number 9 next. And here's what we're going to get for the first one. X is tending towards 2, then we'll get 2 to the power 2. So that's our visualization of limit law number 9. If this was x power 30, it would be the same idea. If it was x power, say, 5, same idea as well. Now we do the limit as x tends towards 2 for f of x, which is back to the kind of problem we were doing all along. We're interested in what happens around 2, so we go to 2 on the x-axis for f of x. It's diving down to a height of around -1 on either end we're looking. getting closer and closer to -1. So that means the limit on this one is -1 itself. Now we're done. This is just a glorified 4 times -1, and we get a value of -4 altogether. We have another weird one to take a look into, but any questions or comments so far with that first one here? Okay, this one looks funny, right? This is like the odd one out. There's no limit operator around f of -1, but that's by intention. Here, the concept is we have to be aware of sometimes it's a true function evaluation, not a limit, like in this case. So if we go to rewrite this, we can say, well, f at -1, go to -1 here on the x-axis. We pass through the hole and we output a value at height 3. So that's all that happens to f at -1, just an ordinary function evaluation. Now the solid dot matters because it wasn't a limit in the first place. Then we turn over to this one. We're heading towards -1, but it's in the limiting process. We're around -1. But you know, it's not too big of a deal. As we get closer and closer to -1, this function is well behaved. There's no holes, breaks, sudden jumps. The closer and closer you get to that -1 value, the closer and closer you get to the height of 2 on this graph. Let me remove that hash mark there. So this will just be +2. That means on this one, we didn't use a limit law at all. This was just a kind of a mixed problem for the sake of review, similar to the stuff we did on section 2.1. We get a value 5 altogether. And major takeaway on this problem is it is pretty visually busy because of the 2 graphs, multiple limits that we're taking as well. That's all about introducing ourselves to all these different limits and see how they work in this kind of context. Well, any questions at all, folks, with this warm-up topic, kind of connecting back to 2.1? Okay, so major tools in these limit laws are how you combine functions algebraically. The sums become sums of limits, same with differences. If you multiply by a constant, you can just put that constant there. We'll use this later on in the notes. Multiplication, division has similar properties as well. And notice the last limit laws are just different algebraic kinds of things. Limit law 8 and 9 are essentially the same. If you put power 1 here, and limit law 9, you're getting limit law 8. And limit law 10 says it works for nth roots. And if it's an entire function inside there, it still works. You can just take the limit and take the limit of the function on the inside. So we're not done with these. We're going to continue to call these up each time we use them. But let's move on to the next big topic. Some functions are just a lot nicer when it comes to limits than other functions. They are the polynomials. In fact, that's a polynomial, x power of n. It'd be an nth degree polynomial. Or the other nice functions are rational functions. This one's rational because there's a polynomial in the numerator and a polynomial in the denominator. So these are going to be the nice ones to take limits on. Tynan says for the 5th practice problem, why would we use limit law 4 and not limit law 3? Well, let me take another look at that one. So 1, 2, 3, 4, 5 should be this one right here. And on the limit laws, use limit law 4 and not limit law 3. Oh, that's a great question. I see what you're saying there. For the limit law 3 problem, let's put this into the notes just as an additional topic so we can see the difference between the two of them. So let's park right here, put it in the middle. How does limit law, maybe not in the middle, let's put it to the left. How would limit law 3 go? It would be for something along these lines. Take the limit as x tends towards a, and notice that c is a different kind of quantity. If we go back to the limit laws, let's look up what it says about c. Suppose c is a constant, so that's the major hint to what's going on there. It means our c value is something like maybe the number 10 for an example. So we're taking 10 times instead of x squared times a function f of x. Let's highlight that so we can see both of them in context. So for this additional example, if we were to use limit law number 3, the way this one will work is, because it's just a constant, x doesn't show up whatsoever. Here it was a bona fide function, so we had to use limit law 4 instead. But the constant says through limit law 3, this is 10 times the limit as x tends towards, I put a there, but I actually want the same value as the fifth example. Let's put 2, so it's the same as before, of f of x. And this is the major action of limit law number 3. That's great. It might kind of remind you of something like some topics with logarithms, although its property is not identical. Something gets moved on the outside of the limit operator, but only if this is strictly a constant. If it was 10 times x, 10 could move, but that x would stay right in position. Does that make sense with that issue there with limit law 3 so far? Awesome. Thanks for asking about that one. That was a great clarification because it's all about the difference between when something is a bona fide function that changes with x, like x squared, the value depends on x itself, and when is it constant? In fact, that's such an important topic. It kind of makes or breaks the day when we're in chapter 3, looking into other methods. Knowing the strict difference between a function that varies and a constant like that can make all of the difference in later on topics. Let's finish off this problem just because we started. We might as well finish it. This will be equal to 10, the constant, multiplied by the limit of f of x as x tends towards 2. We did that limit once already. Right here, we got a value of -1. So this would just result in a value of -10 altogether. Other questions or comments so far? Okay, let's try out the next most awesome property, the direct substitution property. Essentially what the direct substitution property is telling us is, let's look at that equation there very closely as we look at limit laws, say 8 or 9 or even 10. Limit laws 8, 9, and 10 are just saying you can plug in the value where x is heading towards. Limit as x tends towards a of x power of n is a power of n. That works for lots of functions, both the polynomials and the rational functions. As you tend towards a, all you have to do is plug in the value and get a result. It doesn't always work, so we're really interested in the entire classification of functions for which it will work. So let's look into first the rational function. The rational function in this problem is this one right here. It's a ratio of a polynomial divided by a polynomial. So if the value a from right here, in our problem, the a value is 0, is in the domain of that function. So when I plug it in, I'm not dividing by 0. Then the limit is just a matter of plugging a inside the rational function itself. It's just a function evaluation. So if you have a rational function, this is all you have to do. 0 is going to go in position of wherever x is. So here we have x squared minus 2 times x. Divide by x squared minus x minus 1. I put a little parenthesis for wherever x was. Plug in the value 0 through direct substitution. Then just do the normal computation. This is 0 divided by -1, which results in 0. Our work is completely done right at that step. So this is what we finally mean by limits, the algebraic methods. We never even took a look at a graph at all on this one. We just observed that's a true rational function. 0 is in the domain because we didn't divide by 0. And so all of the work is complete right at that step. Kind of fantastic in a way. If we wanted to connect back with what we were doing, looking into graphs, this is what it would look like. Here's the f of x. It's going to be x squared minus 2x divided by x squared minus x minus 1. We're heading towards 0. And as we get closer and closer to 0, the height of the function is getting closer and closer to 0 as well. So that's why the limit outputted is 0 overall in this one. Haley says, if you get an undefined answer, would that mean the limit is not defined? Not necessarily. That's where it's going to depend on the function itself. And that's what's going to go on with this property right here. If we do get division by 0, we might still be able to compute the limit. So we're going to make this theorem do that magic for us and see what happens. Notice as a preview to go along with that comment, if you plug a 1 on this, it's 0 divided by 0, but this limit actually does exist. And we'll show just exactly how to compute it next. Other questions so far?
Well, we did on this one. X and for 0, we direct substitution in for all the x value.
Exactly. We put in that value 0. If it was x tends towards 5, we would have put 5 everywhere where it's highlighted in yellow. Exactly.
Okay, what number was that?
This one wasn't on the list, actually. It was a brand new idea, the direct substitution. Thanks for asking about that. Other questions at the moment? Okay. Well, we mentioned a rational function is a polynomial like y equals x squared or y equals 2x plus 5 divided by another polynomial. And if we look at part B is not a polynomial. It's unfortunate, but, well, there's a constant multiplying a square root. Inside that square root, there's absolutely a polynomial. So part B is one of the opportunities where we get to break this down just a little bit before we even get started with direct substitution property. So let's cite the properties we use as we go through on this one. First, here's our big list. Imagine you're doing this as a quiz, or maybe you're reviewing for an exam. You're looking at this limit. Well, this is going to be somewhere on the last page of the first exam, a resource on the limit laws. And if you spotted that constant, that would tell you limit law number 3 is a good one to start with. So let's say that here. Limit law 3 is going to handle any confusion with that constant by moving it in front of the limit. So let's break this down instead of doing a lot at once, just to see how this works. Using limit law 3 means we'll have 5 times the limit as x tends towards -3 of the square root of the polynomial function x squared minus 2x. Gets us started. We're on our way with this one, but still, I can't use this direct substitution property as it's stated, because if you start with a polynomial like x squared minus 2x, but then you square rooted it, it's no longer a polynomial. It's some brand new function composition, new class of function. So what do we need? A brand new tool like, say, limit law number 11 is a great one. In fact, let's put this on the notes to help us visualize it. You know, it's concerning if I copy limit law 11, but I don't say the provisions we require for limit law 11. So let's put in the full statement here. Just as a reminder, n has to be positive, n has to also be even, so we're not getting into complex valued results. And the thing inside, if it's even, must be positive as well. Okay, so here's limit law number 11. We're going to use it right on this step. So limit law 11, notice what happens with this limit law. It's kind of cool in a way. The nth root function is a complicated one, but the limit operator goes inside of it. It passes right through the nth root of the function. You take the limit of the function on the inside. So in our problem, here's how we're going to visualize it. F of x is the polynomial function we're working with. This turns into 5 times, because the 5 is still part of the problem. This is a square root, so the index n would have been 2, a positive index. So the limit on the side has to be positive, so we don't get a complex result. We have limit x goes to -3. Now on the inside of x squared minus 2x. So that's the action of limit law 11. Sometimes limits pass through structures like nth roots like this one. But once you've done that, here's where the direct substitution property takes hold, right here. Let's make a note here. Now, use the direct, all right, sub for substitution, property. It became a part A type of problem. All we're going to do is take the value of -3 and just plug it in where x is, here and here. So the problem is finished when we go that this is equal to 5 times. In place of x, I'll use the same strategy as before and just put in a placeholder. So that's x squared there minus 2 times x. We're taking that limit of x squared minus 2x as x gets closer and closer to -3. Or direct substitution allows us to just simply plug it right in. Kind of nice in a way. Polynomials are really nice functions. It's sort of messed up because there's a square root. Property number 11 rectifies that for us, and it still allows us to do this valuation. All that's left to do now is just get the number out for this one. So let's start just doing the algebra side of this. This is 5 times the square root of 9 plus 6 altogether. So this is 5 times the square root of 15. Doesn't simplify any further. Let me put a box on this one because I have stuff above and below it, just to emphasize this is where the answer would end. So the direct substitution property is awesome when it works, and it's tragic when it fails, but we have another big tool in this section for when that occurs. When can it ever fail? As Haley was hinted, what if we did get a 0 on the bottom? That limit might still exist, and that's where we're going to combine direct substitution property with yet another property, the next, pretty much the last major result in these notes. But let's catch our breath. Any questions or comments at the moment? Okay, so I put it here on definition 1. Just a reminder, this is back from section 2.1. So back when we first looked into the definition of the limit, the reason we have this here, just pasted in from section 2.1 is there is one graph, well, set of graphs from 2.1, which is really relevant to what we're about to do. And it was these graphs. This is kind of a weird problem because we have 3 functions that look so close to identical. Let me make just a couple small changes so when I take the screenshot, it doesn't look too busy. Well, some of these aren't coming off too easily. Sometimes these digital tools are kind of finicky with what it allows you to do. Okay, so I wanted to put this in as a screenshot. Let's take the comment in as well. Okay, so we did this as our, I believe, second example to start out the course. The reminder is by the red dot. If you say the limit as x tends towards a of f of x takes on a number, that just means the values of f of x, the height of the graph itself, gets closer and closer to the number L in green as the x values get closer and closer to the number a in blue. So on all 3 of these graphs, x is tending towards 1 from both sides, and the function value is getting closer and closer to a height of 2. Doesn't matter if there's an open circle, because the effect of the limit does not matter when x tends towards 1 for this particular problem, or if it's defined in a weird way, or if it's completely plugged in. That didn't copy in for some reason. The limit is 2 each and every single time. Let's make sure it I think I just deleted that on accident when I was copying it. So here's the next interesting thing we can say. Oh, let's bring in this really major tool as well. Let's highlight this to just emphasize this theorem gives us a lot of power. It says if f of x is equal to g of x, when x is not equal to a, the a value that we're concerned about in this problem is 1. And yeah, the function f and the function g and even the function h, they're all equal as long as you ignore what's happening at 1. That's the only difference between all three functions. So if you have equal functions when x is not equal to the value 1 in this problem, then the limits are identical. But that's what we saw. The limits came out exactly the same on every single one of these, because when we take the limiting process, we weren't concerned about what happens around 1, or excuse me, what happens at 1. We just care about what happens around 1. So we did this limit visually for 3 different functions. We got the value 2. Now let's imagine this was the first problem you see in WebAssign, and you didn't have those graphs above. How would we use our limit laws, the last theorem, and the direct substitution property we were just working with all together to do this limit? So this is like our very first big problem in this section notes. We'll do carefully. Then we'll look at another class of related examples down the line in the notes. Use the theorem above to evaluate the following limit. First, direct substitution's off the table. It is a rational function, but if I plug in 1, we'll get 0 divided by 0, and that's a plain undefined. The calculators don't want to have anything to do with it. Let's just put it here for emphasis. 0 divided by 0 is a big problem. But that limit should exist. In fact, we're looking at the graph right here. We see the limit exists. We expect it to, because that's what we've been doing for this whole course up to date so far, finding the limits on these graphs and seeing what happens. That open circle there is just the fact that we get 0 over 0 when we plug in the value 1. So here's what we actually do for this kind of problem. Say again, it's the first problem on WebAssign, or maybe a question on exam 1. We start by factoring. We want to reduce this function into something just a little bit more manageable. We'll take the limit as x tends towards 1 of x squared minus 1 factors as x plus 1 times x minus 1. Divide that by x minus 1. And now we have this cancellation. X minus 1's cancel. We actually made a big comment or a big deal about this in section 2.1. When we cancel off these functions, or cancel off those factors, we're actually changing the function. Now we're taking the limit as x tends towards 1 of just x plus 1 itself. So this was the original function, f of x. Sorry, let me get my red dot going. F of x right here. When we cancel, we get a new function, x plus 1. That's the g of x function we see right here. Let me switch around this color coding just so we can focus more on the functions f of x and g of x. So here's the whole actual function f of x, but we changed it to an x plus 1 function. That's h of x, a whole brand new function outright. But that's okay. This theorem says you can swap functions if there's only one problem right around x equals a, but they're equal everywhere else. We see that on the graphs above. The limits will be the same. So this equality right here is conveyed down in the actual problem we're doing right down here. It tells us we can just simplify, swap out the function to something nicer, and now it's a polynomial function. We can use direct substitution right here. Use direct substitution. We're taking the limit as x tends towards 1, so right where x is here, plug in a 1. This becomes 1 plus 1, and the value is 2. But we were expecting 2. That's what we got on the limit for the one on the left, as also the one on the right at the same exact time. So taking the limits of these functions just boils down to you need an algebraic trick, some kind of trick, and we'll look at different scenarios. The big idea with this one was factor first. Once it factored, we can clean it up. Now it's a nice rational function where there is no 0 divided by 0 issue, and we get a clean limit out the output of this one. Well, any last questions at all, folks? Finalizing this big idea here. Okay. Well, there's lots of stuff going on in this section. We have all the limit laws. You also have the direct substitution property at the same time. And then this all-powerful theorem right here. Really, this is the major workhorse along with direct substitution. And what we're going to do in the notes when we come back on Thursday is just practice some more scenarios out. This is the same theorem as above, just copied down for easier reference. We'll see what happens when we look into just slightly different scenarios. The functions will change, which means our strategy algebraically will change as well. And then we'll go into an application where I had to make an edit on this. Sorry about that if you printed this out already. The revised edit is available on the Canvas page as well as the Blink lecture notes as well. But we'll call it a day here. I don't want to rush through a problem in 3 minutes. That sounds like a big rush. Any last questions at all, folks, before we call tonight? Okay, well, I'd say take a look at what's going on in this section 2.2. Come back on Thursday, and this will make a lot of sense, I'd say. And what's going on in the next section 2.3, continuity? Big hint is continuity is literally direct substitution. We're trying to collect into one category. What is the classification of functions where you can use direct substitution every time? It's the continuous ones. So that's what's going on in 2.3, really just leading off of 2.2 in a direct way. But have a great night, folks. We'll do more problems just like these when we come back on Thursday and likely start the continuity section as well. Take care. Thanks. Have a good one.